Now, this is a well-known or famous Bellman expectation equation. And if you want to solve for MDP, we are going to use this equation. Okay. Now, what is this equation? We're going to talk about it now. The state value function can again be decomposed into immediate reward plus discounted value function of successor state. You see here? Because if you are in a particular state at time t, now you are going to get into a new state, st plus 1. And when you are here and then you take an action, you get a reward. And then you are going to evolve into a new state. So how good is this state? This state has a value. It's like every state has a money associated with it. You just want to evaluate how much money is associated with a particular state. If you want to give it a value, assign a value to a particular state, this is called value function. Then time t and to time t plus 1. But in the middle, you get another reward, right? So what Bellman equation does is actually connect the current state and the next state. And this is, we call it iterative update. Okay? So that later you can compute the value function. So the action value function can similarly be decomposed. Now, you see here, this one connects st with st plus 1. But over here, we are connecting st80 to st plus 1, at plus 1. Okay? That means this is a connection between q and q. This is a connection between v. Okay? This is a v of the current state. This is a v of the next state. This is a action value for the current SA, and this is for the next SA. You choose. Now, if we look at the first equation, you see, Bellman equation has two equations. One is for the value function, the other one for action value function. Now I'm going to show you the connection over here between st and st plus 1. You see, if you are looking at s, this is your s, and then this is your st plus 1, s prime. And if you are in a particular state, okay, and you have multiple actions to choose, and then if you choose a particular action, you get into a new state. Make sense? But here, you not only have two actions. You might, in this action, you might choose a bunch of, in this state, you may have multiple actions to choose. So this circle denotes the state. This solid black dot denotes the action. And then, once you choose action, immediately you got a reward. And then you evolve into a new state. So this is a state. This is action. This is a new state. Make sense? So the first set of equation is trying to connect state with the successor state. And later, the next slide, we're going to connect, we're starting from the action. You see, here, we're starting from action and then connect with action. But here, we're connecting state with state. We're just looking at the same diagram. But over here, you also have action, right? So the next one is actually connect from here to here and then to the action. But here, we are connecting state to action and then to state. Yeah, Omar?
The reward, it depends not just on the, does it depend just on the action or the action and then the probability of which state we end up with?
Well, of course, this is a state, right?
Yeah.
In this state, I choose this action, I get a reward.
Yeah, but the reward has a probability equal to the probability of going.
And then you have you are going to evolve into different state.
But the reward is different between these two branches. Like the branch that goes to the one on the left and the one to the right.
This reward actually only depending on this S and A. It doesn't depend on the future state. Okay. So once you are in a state, you choose an action, immediately you get a reward. You see here, these are actually depending on the S and A. Let's look at this equation more in details, then we discuss this, okay? You see here, this is your current state. You want to estimate how good your state is, the current state is. And now, this you have a pi, right? What is pi? Pi is a policy. And you're going to take the expectation over your policy. And then you have RT plus 1 and gamma V pi ST plus 1. This is the next state. But in this process, it's more complicated than this, just this equation. But let's expand this equation a little bit. First, this is still my value of my state. Now, when I'm in this state, I have multiple actions to take. So since I want to take the expectation, then what I do is I need to average over all possible action I'm going to take. Does that make sense? Yeah. That means over here, in this state, I'm going to choose different actions. I have probability to choose different actions. Is it right? In a particular state, I have probability to choose different action. Then, when you choose the action, you're going to have a value. This dot actually has a value associated with too. So what we do is, if you choose a particular action, now you have an action value. That means this probability times the action value gives you the expectation.
So it's kind of like a decision tree.
Yeah, this is decision tree. This is probability decision tree. Basically, this. Now let's finish this part before you ask any questions. So you have a state. Now you have an action. This is a probability to choose a particular action, and then the action has a value, right? Q is the action value. Q is right here, and this is V. This is Q. We are having a pi to choose different actions. Now for each action, I have a value. Then I just use probability and then times the value I got. This is the expectation. Now, but this Q is actually equals to a particular RSA. Okay? If you are in the S, you choose a particular action, you got RSA. And then, however, it also depends on what state you are in. What state you are going to be in the future. So this part actually has a different value. That's what you meant by the the branch value, right? Yeah. The branch value is actually this one has a value. Okay. Now, this QSA equals to RSA. Okay. RSA, and then gamma. You have a. If you are in state S and then you choose a particular action, but that's still randomness, you can get into different state. And then different state has different value. Okay? Make sense? That means we're going to take expectation over here.
Yeah, I think my confusion was, do we make the action like in a deterministic way, and then there is a stochasticity after making the action that we end up with this state or that state, or is it there is?
No, it's not deterministic.
An
so here, when you take the action is a pi, defined by pi. So that's why it's a probabilistic way you're going to choose an action. So this is my policy. That's why we have the first sum. This is the first sum. And even if you choose a particular action, you still have probability to end up in different state. So this is another expectation of the value of the future state. You want to average over that so that you get a general idea if you are in the state A, S and A, and then what's going to be the, and then you have values of your successor state too. Okay, make sense? So this is value, state value. This is action value, and this is a state value. And later, let's see how action value and state value and action value, they are connected. Okay, here we're trying to connect the state value and the state value together. And the next slide will be, this is the action value. Okay, and then you have S and A. Okay, and then you have the probability to end up in different S prime, even if you choose this action, this particular action. You still have probability to end up in different state. Am I making sense? So the Q pi SA and connect to this Q, connect to this Q. Okay, so this is the action value for this SA. This is for the S prime A prime. This is for T plus 1. This is for T. Okay. Now we have the first expectation. Okay, and then this is an expectation. So Q pi SA equals to RSA, and then plus gamma. You see here, okay, we choose the SA. Then immediately we get a reward. And then we will end up in different state, right? S prime, different state. And each state has a value. And however, this is a random policy, right? So we need to, because the randomness, stochasticity, okay? It's not deterministic. It's not like you are in one state, you choose an action, then definitely you're going to be S prime. But S prime has many possible S primes. You are in this state, you choose this action, and you could end up in different S primes. What do we need to do? This is a transition probability. You're in state S and A, and then you end up in S prime. But S prime has a value. This one has a value. This one has a value. So you want to average. No, not average. This is an expectation. It's not a simple average. Okay, this is an expectation. Expectation is like a weighted average based on the probability, based on the transition probability. So that's why. So this equation right over here, up to this point, we only consider to over here. We only consider this black and this white circle. White circle is here, and the black dot is right here. And then we're going to expand this V pi S prime. How to expand this V pi S prime? Everything here, we don't touch it. But a V pi S prime, this V pi S prime is actually equals to pi A prime given S prime. Because over here you are going to have a policy, right? Policy to choose different actions. And then what is the probability to choose this action, and this action? It depends on the pi. So we're going to do another expectation of I choose different actions, then this action has a value. So this is action value to action value, but we put the state value in between. So this is like state, action, state. Okay? The previous one is, no, this one is action, state, action. Previous one is state, action, state. But if you look at this part, this red color section, it's actually what is right here. Because this part is actually the same as the second part. Make sense? So this is like a hierarchy. And you can have state, action, state, and then you have action. In the next slide, we are looking at this part. Action, state, action. But in this slide, we are looking at the first three levels. And then you can extend to the next three levels. Okay? But they are connected. It depends on what we are looking for. So that's why later we have Q and learning, and also state, the Q learning, and also the SASA algorithms. They are all depending on, SASA means SASA, S-A-R-S-A. SASA means state, action, reward, state, action. So this is called SASA. Okay, the famous SASA algorithm. So this is look inside the expectation. So Q pi S A, action values. This is look inside the V. So we look just start from V, and then we look at the two more levels. We want to connect the successor. So this one is also, you see this one is connect the successors. Once you can connect the successors, you can use iterative algorithm to do the update. So that's why Bellman's beauty, the beauty of Bellman's equation is the connection of the current state with the next state, and then connection of the current state action with the next state action pair. Now we got this equation v pi. You see here, the Bellman equation can be expressed concisely using the induced Markov reward process. You see, this is v reward plus gamma transition and then v. This is for state value function. If you look right here, this is v reward and then v again. Okay? If you write it for all the state, then it will become a matrix. It will become a matrix. Oh, this one is a matrix, and transition probability matrix is a matrix. Then you can solve for this equation. And how to solve it? This is only for small, very small state space. And then you can do this. Okay? And then what we do is you just move this v pi to this side, and then you do the inverse. You see? You got it. You solve it. You actually solve for the v. Okay? And this is a prediction. So up to now, we were given the policy. Okay? Policy is giving me the state, what's the probability to choose a particular action. We have already been given the policy. We're just predicting how valuable my state is, or my states are, right? What is the state value? But the next one is, not only you want to find the value function, but also based on what you find, you want to find the best action. Because if you can define the action, that means you have a policy too. So here, you see here, when you are in this state, you have possibility to choose different actions. Now, instead of doing the expectation, I'm going to choose the best action. So this is the optimality equation. So V star S is actually equals to the max. Now, why I put this one over here? Because you have a choice to make. The choice you're going to make is this max. You're going to choose the actions that maximize. So you see here, if you are in this state, you have action value, and different action values. Now you want to choose the action, okay, that give you the maximal action value. So this is why I have this one. You choose the maximum one. So, but you can expand this part. This is RSA plus gamma, and then you have probability to getting to different state. You have another expectation to make, because in order to calculate this action value, I need all the state values, and then doing the expectation over the state values, I got my action value. Okay. And this one, this is an optimality equation for Q star. You see, for Q star, now we're gonna, you have already in this state action pair. Now you are getting to a new state. Now over here, you have a probability to choose which action to choose. Okay. So Q star A equals to RSA plus, of course, you are doing the expectation over all your state. But for each state you are getting into, then you have a probability to choose different actions. That means you're going to choose action over here. Okay? So RSA plus the probability to getting to this state, and then what is the value of this state? Okay, and then this will equals to the max QSA. Then when you are in this state, you actually choose the action that give you the maximum action values, instead of just doing the expectation over all the action values, all possible action values. You see here, V star S prime. Basically, we're just putting this equation here. Instead of writing everything for the second level, once we get to the V star S prime, we just directly replace that with the best or the maximal action value. Make sense? So this is the second part. So optimal policy. We're going to define a partial ordering over policies. So if pi is better than pi prime, that means the value function is greater than v pi prime s for any s. you choose any state, you find that this policy is better. That means the state value function is higher. For any Markov decision process, there exists an optimal policy pi star that is better than or equal to all other policies. So what you want to do is find the best policy that you can get. And all optimal policies achieve the optimal value function. That means V star. And all optimal policies achieve the optimal action values too. So finding an optimal policy is by maxing over. Okay. So if you have already got a QSA, of course, finding the best policy, now you are not, instead of making this probabilistic, you are going to choose, you're going to make it 1. Now you're making it 1, okay? All other actions, they will be 0. The probability to choose all other actions will be 0. And you are only going to choose the actions that give you the best value, or give you the maximal value. So that means if you want to define an optimal policy, how do you do that? If you know Q, you know the best policy. That means what we want to calculate is QSA, the action value. Because action value is defined for an action. If you know how good the action is, of course you choose the best action. So that means you are going to use the recursive equation to calculate either Q or V. You know, Q is relevant to V. Because if you know V, you know Q. Because Q, right? Q is relevant to V because they are just different levels. If you know V, immediately you know Q. If you know Q, you know how good the action is. You just choose the best action and making everything else to be 0. There's always a deterministic optimal policy for any MDP. If we know this one, immediately we find the best policy. So solving the Bellman optimality equation, there are different ways. Okay? In general, there is no closed form solution. We can use iterative solution. Iterative, you see, iterative. Because this is iterative, because the state value function is iterative, and action value function, Bellman equation is iterative. So all these solutions are based on the Bellman equation. Okay? So that's why if we know Bellman's equation, we pretty much know how to solve the MDP, if we know it well. Finding an optimal policy by solving the Bellman optimality equation requires you know the accurate knowledge of environmental dynamics. What does this mean? That means you need to know the transition. You need to know the transition probability matrix. But in real world scenario, many times we don't know the transition. So that's why for some of you, you need to estimate what is the transition probability, right? So we have enough space and time to do the computation. And also the Markov property should be satisfied. But whether Markov is satisfied or not, depending on how you define your state. You want to put sufficient information into the present state so that Markov property can be satisfied. So how much space-time do we need? Polynomial in number of states. Because you see, you need all the Vs. If you have 10 states, that means you need a safe space for all the 10 states. And then you update to the next iteration, right? So but the number of states is often huge if you have 1,000. So exhaustive sweeps of the state space are not possible. Okay? So we usually settle for approximations. If you want to know more about approximate ADP, approximate dynamic programming, you can read the book by the Artificial Intelligence Neural Network to Approximate Bellman Equation. Pretty much, that is what AlphaGo does. AlphaGo uses the neural network to approximate the V function and the Q function. Okay, because the state space is so high, okay, so huge, so that they cannot really settle down for precisely, like explore all the possibilities. So they use neural network to learn, to build a function to represent my state value function and the action value function. So this is an effective mitigation strategy for reducing the impact of dimensionality by replacing the memorization of the complete function mapping. So you see, this is a function mapping. You know what is a function mapping? You have S. I give you a value, and then you replace it with a neural network. If I give you S and action, and then you use a neural network to tell me what is the action value. So this is called, no matter you are using the multi-layer perceptual neural network, or you are using the deep learning neural network or convolution neural network. Convolution neural network is for the image, okay? Okay, if you have an image, multi-dimensional space or three-dimensional convolution or two-dimensional convolution, you use deep learning. And I see some people use like only they don't have an image, they call it convolution. I said, what? And I don't know what they are convoluting. But the whole space domain with memorization, but you are replacing it with a neural network to do the work for you and settle down for the approximation.